So welcome to Everyday Mathematics. Today's problem comes from MIT 2024 Integration Bee Quarterfinals number 3, and our problem of focus is problem number 2, which is the definite integral from x equals to 0 to x tending to infinity of 1 over, in bracket, x plus 1 times, open bracket, log x to the power 2 or log x squared plus pi squared. It's a very interesting problem. I hope you enjoy it. Before I jump onto the solution to this problem, I'd like to thank our subscribers. Thank you so much for your support. We don't really take your support for granted. We really treasure your support. It's your support that motivates us here to come here time and again. For our first-time visitors, what we do at Everyday Mathematics is we go about and look for these interesting problems like one we have here today, and then we try and solve them, and then we come back and share the solutions with you. For our repeating visitors who haven't yet subscribed, our plea to you is that please do consider subscribing to our channel. I think it's an awesome channel, and we can learn a great deal from it. Then now going on to the solution to this problem, the first thing that I would like to do is I substitute for the most complicated expression, and that is log x. I'll say let u be equal to log x such that e to the power u equals to x. And so eu du dx, e to the power u du dx is equals to 1. And therefore you could substitute for dx with e to the power u du. And so when also x equals to 0, what that means is that log x tends to negative infinity. And then when x tends to infinity, that means that log x also tends to positive infinity, such that the integral from x equals to 0 to x tending to infinity of 1 over x plus 1 times log x squared plus pi squared is equals to the integral of from u tending to negative infinity to u tending to positive infinity of 1 over, in place of x, we're going to put this e to the power u plus 1, and in place of log x squared, we're going to put u squared plus pi squared. Now we can also go ahead and now pull this e to the power u here. I beg your pardon, I had forgotten to indicate that in place of dx, we can put eu du, e to the power u du. And so pulling this here so that now we have e to the power u over e to the power u plus 1 times u squared plus pi squared. The interesting thing here is that we can now split this integral as the integral from u tending to negative infinity to 0 to plus the integral from 0 to u tending to positive infinity. So we have two separate integrals. And it's the same integrand here, but we're just changing. We're trying to split it into the positive and the negative half of the interval, or the integration interval. Now, what we can do here is, in order to change this into the positive domain, what we're going to do, we can just say let u be equal to negative u, such that wherever you see a u there, we have negative u. So you see e to the power u, we have e to the power negative u. E to the power u here becomes e to the power negative u. And since it's u squared here, this is even. So it's the same both in the positive and the negative interval. And then since du becomes negative du, so this negative here is shown here. And in order to cancel that negative, we can flip the interval. So we have the integral from u equals to 0 to u tending to positive infinity of e to the power negative u over e to the power negative u plus 1 plus times u squared plus pi squared. And then the next thing we can do for the second integral here, we can divide both the numerator for this second integral by e to the power u. And what that becomes is the numerator becomes 1, and the denominator here becomes 1 plus e to the power negative u times u squared plus pi squared. Now, combining those two integrals together, we have now in the numerator, 1 plus e to the power negative u. And so as you can see, this and this cancel out, and we are left with the integral from u equals to 0 to u equals tending to positive infinity of 1 over u squared plus pi squared. And as you can see, this is the simplest integral now that we can handle. We'll just say let u be equals to pi tan theta. And so du d theta is equals to pi sec squared theta. And so we can substitute for du with pi sec squared theta d theta. And when u equals to 0, what that means is that pi tan theta equals to 0, and therefore theta equals to arctan of 0, which means that theta equals to 0. When u tends to positive infinity, pi tan theta tends to positive infinity, and tan theta tends to positive infinity, and therefore theta tends to pi over 2. So our integral now of u equals, from u equals to 0 to u tending to positive infinity of 1 over u squared over pi squared is the same as the integral from theta equals to 0 to theta equals to pi over 2 of 1 over pi squared in tan squared theta in place of u plus pi squared. And then here in place of du, we have pi sec squared theta. And so we can now do a couple of things. We can pull out pi squared here in the denominator and also pull out the pi in the numerator. And we have 1 over tan squared theta plus 1 sec squared theta. This part here is the same as sec squared theta. And so this 1 cancels with this squared here. And so we have 1 over pi times the integral from u theta equals to 0 to u theta equals to pi over 2 or 1 over sec squared theta times sec squared theta. So this and this cancel. So we are left with the integral of 1 from theta equals to 0 to theta equals to pi over 2. And so that's 1 over pi, and theta there is what is been obtained by integrating 1 with the interval 0 and pi over 2. So that's 1 over pi times pi over 2 minus 0, and that is 1 over pi times pi over 2. These pi's cancel, and so we are left with the half. And this is our answer. Very interesting. So that's how you solve this question. I don't think it was super complicated, but it was definitely very interesting, and it needed you to do some little acrobatics here and there to be able to get a more tractable problem. And so thank you so much for following along. Until next time, à tout à l'heure, à la prochaine fois. Adios.